Okay. Today we're going to take up power relationships in AC circuits. So it's an extension of what you learned the last, yeah, I guess the last 2 weeks, which is AC circuit analysis, the the Phasor method. I'm going to be presenting a lot of math this afternoon. Um, Actually, at the end of the day, it's not really the math that's important, but it's an understanding of the concepts. Unfortunately, I have no choice but to present the mathematical basis for all of the relationships that we're going to take up this afternoon. What I attempted to do was, if you take a look at the material that was distributed by the handler in charge of this module, it's quite lengthy. Have you had a chance to take a look at it? Who has had a chance to take a look at the material? Be honest, no? I won't take it against you kung hindi pa. Who has had the chance to look at the material? Meron na ba? Okay, it's quite lengthy, no? So what I try to do is I try to condense it into the most important um, slides, no? Um, but if you really want a more comprehensive reference, then go to the material that was published by Dr. Nervis. No? Dr. Nervis is the handler in charge of this module. Okay, so let's begin. Okay, so this is what we're going to take up today: power in AC circuits. This is one of two parts. Today, I'm going to present the concepts. On Thursday, it's just really going to be mostly examples. Okay, here's the situation. Let's say I have a sinusoidal source, and this is supplying power to a passive network. Passive network consists of resistances, inductances, and capacitances. If my voltage source is sinusoidal, expect a sinusoidal current to flow. If my voltage is of the form V of t is equal to V of m cosine omega t plus theta v, where theta v is the phase angle of my voltage, expect a sinusoidal current to flow. That current will be of the form I of m cosine omega t, okay, the same omega, plus theta I, where theta I is the phase angle of my current. So you input a sinusoidal voltage, expect to get a sinusoidal current. In general, your voltage and your current will not be in phase with each other. That's why they have different phase angles. Okay, what's our formula for power? Power is equal to V times I. You learned that in the first week of this course. No? Power is voltage times current. So this is my expression for voltage, V of m omega t cosine omega t plus theta v. This is my expression for current. I multiply those two together, and I'm going to get what is called the instantaneous power. No? Instantaneous power. This is a power this is an expression for power which is a function of time. Naturally, it will be a function of time because my voltage is a function of time and my current is a function of time. Okay, let's try to take a look at what the plot of that power will look like. No? So this is representative of my voltage, the blue line. This is representative of my voltage, V of m cosine omega t plus theta v. And this is representative of my current, I of m cosine omega t plus theta of I. No? where the phase difference between my voltage and current is theta V minus theta I. The horizontal axis here is omega t. This is omega t. By the way, no, just as a review, and please just shout out the answer. Which is leading here? The voltage or the current? Which is leading?
Voltage po.
Yeah, the voltage is leading. No, the current is lagging. Okay, so how do I get an expression for my power? I just multiply the blue curve with the red curve. And I actually did this in Excel. No? That's how I produced this particular graph. So I just multiplied point by point in Excel, and I produced this particular graph. So this is an expression for my power. Okay. So just some observations. No? So dito, I reproduced the graph for my power. Note that the plot of instantaneous power versus time is also sinusoidal. We had a sinusoidal voltage. It resulted in a sinusoidal current, and the power, which is voltage times current, is also sinusoidal. However, notice that the frequency is twice that of either the voltage or the current. If I go back here, I just did a point to point. So you notice that when the voltage is equal to zero, your power is equal to zero. When your current here is equal to zero, your power is equal to zero. Positive times positive is positive. Negative times negative is also positive. That's why you come out with a frequency that is twice that of either the voltage or the current. There are times when the power being delivered is positive, and there are times when the power being delivered is negative. So if you take a look here, in this particular area here, the power being delivered is negative. On the other hand, dito, from here to here, the power being delivered is positive. Okay, if I go back to my original network, anong ibig sabihin ng power being delivered by the source is negative? What does that actually mean? Can anybody tell me? What does it mean if you say the power being delivered by the source is negative?
The source is absorbing power po.
Yes, that's right, no? Ibig sabihin, the source is absorbing power. But this is a passive network. So how is that possible? Where is the power coming from? No? Can I hear somebody else? Saan nanggagaling yung power na yon? Anybody with any idea?
Sir, yung nasta-store na energy sa inductor at capacitor?
Very good, no? Very good, yeah. So that's actually coming from the energy that is stored in the inductor and capacitor, no? So sometimes the source delivers power to the network, no? But there are times when the network will deliver back power to the source, and this is because the inductor and the capacitor store energy. Okay? However, if you take a look at this graph, and this is typical of power, the average power delivered is generally not zero. In other words, if I take a look at this graph, somewhere here, this is actually the average power delivered. It is generally not zero. So those are just some observations. Okay, now if you take a look at the notes, your notes will go through a derivation, no? A very comprehensive derivation of this. No? Saan ang galing to? Well, this is just this equation. No? Remember, instantaneous power is equal to my voltage. This is my voltage multiplied by my current. If you apply a lot of trigonometric identities, so again, if you're interested, you take a look at the course notes that was distributed. If you apply a lot of trigonometric identities, that expression can be converted into this expression. Now you're probably wondering, this expression seems to be more complicated than the original expression. But this expression actually tells us more information than the original expression. So ito yung expression for P, which was derived from the product of voltage and current that earlier we showed. Okay, what I want to do is, instead of using amplitude, so Vm and Im are amplitude, I want to convert this expression for P using voltages and currents expressed in RMS value. So V, in this case, V is equal to Vm over the square root of 2, right? Pag wala akong linagay na effective dito or RMS, assume that to be RMS, no? So this is implied RMS value or effective value. Same thing with I, no? I is equal to I of m over the square root of 2. Okay? So what happens, no? I replace V of m with V, so that's going to be square root of 2V. I replace I of m with I, that's going to be square root of 2I. So square root of 2 times square root of 2 is 2, and then 1/2. So nawawala yung 1/2, no? So this is my final expression for power, okay, given the source voltage and the source current that we showed earlier. Okay. I'm going to go back to this several times within this lecture. So babalikan ko to several times. No? What did I put here? Okay. Okay, this is just something to note. This is just something to note. There are 3 terms in our expression for instantaneous power. There are 3 terms. The first term is VI cosine theta V minus theta I times 1. Times 1. No? The second term is VI cosine theta V minus theta I times cosine 2 omega t plus theta I. And then this is my third term. Okay. So if I take a look at my first term, VI cosine theta V minus theta I, theta V and theta I are constant. Therefore, this is actually a constant. If I take a look at my second and third term, they are actually sinusoids. Where the amplitude of my sinusoid is ito, VI cosine theta V minus theta I, and the amplitude of my other sinusoid is minus VI sine theta V minus theta I. No? So your instantaneous power consists of a constant term, that's my constant term, and 2 sinusoidal terms or 2 sinusoidal components. Okay. Let's take each element one at a time. No? Let's consider a resistor. Okay. So let's assume that I have this current flowing through the resistor. Again, this is expressed in terms of amplitude I of m. What will be the voltage across my resistor? The voltage across my resistor will simply be equal to R times I of R. So R times I of R. So this is my voltage across the resistor. Rim cosine omega t plus theta I. Now let's try to get an expression for power. Our expression for power is voltage times current. So this is going to be my expression for power. So I'm just multiplying this by this. Notice that's going to be Rim squared cosine squared omega t plus theta I. Now, if you remember your trigonometry, what is cosine squared theta? Cosine squared theta is cosine 2 theta. Yeah, that's right, no? Cosine squared theta is equal to cosine 2 theta. So cosine squared omega t plus theta I is equal to cosine 2 omega t plus theta I. No? So ito, okay. Sorry. Erase yung sinabi ko, no? The identity is something like this. Cosine squared theta is equal to 1 plus cosine 2 theta. That is the trigonometric identity. So cosine squared omega t plus theta I, ito, is equal to this, no? Is equal to 1 plus cosine 2 omega t plus theta I. So I can express my power this way, no? Power is equal to I squared R times 1 plus cosine 2 omega t plus theta I, no? Kung hindi kayo nakakasunod, please just shout out, no? And I'll repeat, no? I'll repeat whatever I'm explaining. So far okay lang ba? Have you been able to follow? Can you shout out your question, no? So that the others can, so that I don't have to repeat it.
Hindi pa ba kasama yung 1/2 dun sa cosine squared?
1/2.
As in, cosine squared theta is equal to the quantity 1 plus cosine 2 theta all over 2.
Over 2. Yeah, over 2. You're right. Over 2. So thank you. Tama. Cosine squared theta is 1 plus cosine 2 theta over 2. Okay, any other questions? Okay. What does the graph of this look like? What does the graph of this look like? No? Just very simply, if I take a look at the power, so this is the power with respect to time, meron akong average value. The average value is equal to I squared R. Okay. And then my power will look like this, no? Where the frequency is equal to 2 omega. The frequency will be equal to 2 omega. In other words, if I had a pure resistor, no, if I had an AC source and a pure resistor R, if this is the RMS value of I, okay, this is how my power would look like. The average value is I squared R, okay, but it oscillates, no? It oscillates this way. That is how and the power delivered to a pure resistor will look like. Okay. Note that the power will never be less than 0. No? Why can't the power be less than 0? Because a resistor is not capable of storing any energy. A resistor cannot give back energy to the source. No? So at worst case, the power will be 0. Okay, I told you babalikan natin to, no? Babalikan natin tong expression na to. So I said to set it aside. Okay, let's compare this expression for power delivered to a resistor to this general expression for power that I earlier derived. No? Let's compare the two. So notice, mapapansin ninyo, this term and this term are the same. No? These are equal. No? These are equal. What does that mean? No? That seems to indicate that this and this will be equal also. On the other hand, dito sa top equation, I don't have any sine 2 omega t plus theta I term. So what does that imply? That implies that this must be equal to 0. Okay, so we can conclude for a resistor that I squared R, and what did we say was I squared R? We said that I squared R is the average power. No? That is the average power delivered to a resistor is equal to the RMS value of your voltage multiplied by the RMS value of your current multiplied by the cosine of the difference in angle between your voltage and your current. That is the average power delivered to a resistor. And we can also conclude that this term, VI sine theta V minus theta I, must be equal to 0. Any question about the resistor before I move on to the inductance? Okay, I take it, nakakasunod pa rin kayo? So let's take a look at the inductor. Again, I'm going to assume the same sinusoidal current flowing through my inductor. What is the voltage across your inductor? Shout out, please. Anyone? Nakalimutan na nyo? Okay, it's just so that we don't waste time. No? V of L is just L, the I of L by dt. So if I apply this formula, I get V of L is equal to this, no? Minus omega L, I of M sine omega t plus theta I. Because the derivative of cosine is equal to sine. So again, what am I going to do? I'm going to multiply my current with my voltage because I want to get the instantaneous power. So this is the expression I'm going to come up with. No? This is my voltage. No? Ito yung voltage ko. And then this is my current. Well, no. My voltage is omega, negative omega L I of M sine omega t plus theta I. Then my current is I of M cosine omega t plus theta I. Okay? And so that's equal to this. So ano yung identity na ginamit dito, no? Sine theta cosine theta is equal to 1/2 sine 2 theta. No? Or sine 2 theta is equal to 2 sine theta cosine theta. So that's just the identity that was used here. Okay, but notice that, okay, omega L omega L is equal to X of L. Right? The reactance of your inductance is just omega times L. And then again, converting to effective value, right? We convert to effective value. In the effective value is I of M divided by I is equal to I of M divided by the square root of 2. Sorry, no. Or I of M is equal to square root of 2i rather. Converting to effective value. This is going to be my expression for the power delivered to my inductance by the current I of L. Notice that the power is negative. Instantaneous power rather is negative. What does this look like? Ano magiging itsura nito graphically? So graphically, okay, I have sine 2 omega t plus theta I. It looks something like this, no? Happened. Forget the face, no? But it's going to look something like this. Okay, where the amplitude, so this is piece of L, no? This is piece of L versus T, where the amplitude is I squared XL, and then this is a negative sine wave. So notice you have a negative sine wave. The frequency is equal to 2 omega. So the power alternates between power being absorbed and power being delivered. Power being absorbed, power being delivered. Absorbed, delivered. So notice that when you have an AC current flowing through your inductance, okay, one half cycle, it is absorbing power. The other half cycle, it is delivering back that power. But the average power is equal to 0. Meaning to say, if I have a pure inductance, isasaksak ko sa, let's say, Meralco outlet ko, sa outlet ko sa Meralco, pure inductance, dapat hindi gagalaw yung power meter ko. Dapat walang mare-register na konsumo ang metro ko. No? Because the average power delivered to my inductance is equal to 0. That's how it's supposed to work. Of course, there's no such thing as a pure inductance. Okay, doing the same thing that I did earlier, ano? So ito yung expression ko for power. Ito yung pinarada nating equation kanina. So I just want to compare the two. Okay, this time, wala akong cosine term, no? I only have a sine term. I have yung sine 2 omega t plus theta I, that's this. So anong ibig sabihin nun? No? Ang ibig sabihin nun, itong term na to, minus vi sine theta v minus theta I, must be equal to minus I squared XL. So ito yun. No? I squared XL is equal to VI sine theta V minus theta I. And because I have no cosine term here, that means this must be equal to 0. It's equal to 0. And we do the same thing with the capacitor. So this is the current through the capacitor. I'm just going to breeze through this. No, it's same lang naman. No? So the voltage across your capacitor is 1 over C, the integral of I sub C dt. So this is my expression for voltage across the capacitor. So again, how do I get instantaneous power? I multiply my current by my voltage. And so this is what I'm going to get. Okay. That's what I'm going to get. And then using my trigonometric identities, I convert that to this form. No? And also knowing that 1 over omega c is equal to x of c. Okay? I convert it to this form. Okay? So ganun din ano, yung power delivered to a capacitor. So this is P of C versus T. This time it's a positive sine wave. And the amplitude of your sine wave is I squared x of C. Dito ano ba? Yeah, I squared x of L dito I squared x of C. Again, the average power is equal to 0. Same implication. If I plug a pure capacitor in my Meralco outlet, no, I should not get any additional power consumption recorded in my electric meter because the average power is equal to 0. And then I do again the comparison. No? So ito pinarada natin to. Ito pinarada natin. So now I compare it again to power. Again, no, same conclusion. This term must be equal to 0 because I don't have any cosine term here. On the other hand, ito, minus VI sine theta V minus theta I must be equal to I squared x of C. No? So I squared x of C is minus VI sine theta V minus theta I. No, ano yung significance nito? What is the significance of this? The significance of this is the amplitude in which my power, my instantaneous power, goes up and goes down. Okay. Same thing with your I squared x of L earlier. No, that's the amplitude in which your instantaneous power goes up, goes down. But again, the average is equal to 0. Okay. Let's summarize. So this is my expression for power. This is general case. General case. This is the case of a voltage source, a sinusoidal voltage source supplying power to a passive circuit. And this is already, V and I are already expressed in RMS values. We saw that for a resistor, this is going to be my expression for my power. For an inductance, this is going to be my expression for my power. And for my capacitance, this is going to be my expression for my power. Note that the resistor, if you take a look, itong power to the resistor looks very similar to the first term here. No? You can see the 1 plus cosine 2 omega t plus theta I. On the other hand, the power delivered to my inductance and my capacitance, so these two equations, looks very similar to the second term, to this particular term. And also take note that net power can only be delivered to resistors. The net power delivered to inductors and capacitors, as I showed in the graphs that I earlier prepared, is equal to 0. Let's get into some definitions. Real or active power. Real or active power is defined as the average value of the instantaneous power. It is the power that is converted to useful work or heat. If I go back to sorry, no? Hindi ko ma-access here. If I go back to the graph I made earlier, okay, this is your real or active power. It is the average value of your instantaneous power. Yan yung real or your active power. No? Okay, let's go back to where I came from. No? Okay, and the real or the active power is the power that is converted to useful work or heat. So this is the instantaneous power. This now, remember, this is the one that is delivered to the resistance, no? Because there is no average power delivered to an inductance or a capacitance. Okay. And the average value of this term, if you take a look at the average value of this term, the average value of this term will only be equal to this, to VI cosine theta V minus theta I, because the average value of this term is equal to 0. So the average, the real or active power is given by this expression, where V and I are in RMS value. Remember that V and I here are in RMS value. Now we use the capital P to denote real power. Okay, so again, these are the instantaneous powers. So from that, we can see that these are the instantaneous powers to a resistance, to an inductance, to a capacitance. We can see that for a resistance, the real power is I squared R. That is the average value of the power that is delivered to the resistor. And the real power delivered to an inductance and to a capacitance would be equal to 0 because the average power is equal to 0. I'm going to come up with our second definition now, and this is reactive power. So recall, these are the instantaneous powers delivered to inductance and to capacitance. If you get the negative of the coefficient of this term, the negative of the coefficient of the sine 2 omega t plus theta I term, that is what you call your reactive power. And we use the symbol Q to represent reactive power. Reactive power is the power associated with inductors and capacitors. So the reactive power associated with an inductance is I squared XL, where I is the RMS value of the current through the inductance. And the reactive power associated with a capacitance is negative I squared XC. Okay. So again, let me go back to this expression. Let me go back to this expression. This is your real power. Okay, the reason being the average value of this is equal to 0. And then this is your reactive power. No, sorry. The negative of this is your reactive power. Okay. The unit for reactive power is VARS. VARS stands for volt amperes reactive. And in general, Q, as you saw in the equation that I just showed you, is equal to VI sine of theta V minus theta I. That is Q. Okay, so pangatlo na to, no? So I defined real power, I defined reactive power. Now I'm going to define what we call apparent power. The product of the RMS voltage and the RMS current is defined as the apparent power. More often, or more commonly, it's called your volt amperes. No? And the symbol for apparent power is S. So S is really just VI, and the unit is VA or volt amperes. If you take a look at electrical equipment, they're usually rated in terms of volt amperes. Sometimes they're rated in terms of real power. Sometimes they're rated in terms of volt amperes. For example, if you're buying a transformer, sa hardware store, it will specify the power capacity of the transformer in either watts or volt amperes. Note that volt amperes is not the same as watts. Okay, S is neither a phasor nor is it a complex number. It's just a scalar quantity. The product of these are magnitudes, no? These are magnitudes. Maybe I should emphasize that, no? Yeah, no, it is emphasized here, no? The RMS voltage and the RMS current, no? So hindi kasama yung angle. Right? Hindi kasama yung angle dito, no? This is just the magnitude of the phasor. The RMS value of V and the RMS value of I, that is your apparent power S. That is not a phasor, nor is it a complex number. If I get the ratio of P, real power, to S, that is what I call my power factor. Right? And since P, if you recall, P is equal to VI cosine theta V minus theta I, and then S is equal to VI. If I get the ratio of P to S, nagka-cancel out yung VI, all I get is cosine of theta V minus theta I. And you call that your power factor. Now, your power factor, you have to specify whether that is leading or lagging. The power factor is lagging when the current lags the voltage. The power factor is leading when the current leads the voltage. So the reference is always the current with respect to the voltage. If the current lags the voltage, it's lagging. If the current leads the voltage, it is leading. When does current lag voltage? That is when the reactive power is positive. Kailan positive yung reactive power? What do you call the type of a circuit? Can somebody tell me?
Inductive po.
Yeah, when the circuit is inductive. No? When the circuit is inductive, your reactive power is positive and your power factor is lagging. When the reactive power is negative, then the power factor is leading. And that happens when you have a capacitive circuit. Okay, so everything that I just talked about boils down to this summary. This is really what you have to know. No? It's good if you understood all the derivations that we did earlier, because it gives you a better sense of what these equations are all about. But at the end of the day, these are really what you have to remember. Itong summary of your power equations. And what are these? No? First of all, real power. Your real power is the RMS value of your voltage multiplied by the RMS value of your current multiplied by cosine of theta V minus theta I, no? Where theta V is your phase angle of the voltage and theta I is the phase angle of your current. That is your real power. And for a resistor, this is I squared R. No? Yeah, it is I squared R. Okay. What is your reactive power? That's Q. And that's VI sine of theta V minus theta I. And the unit is VARS. Ano ibig sabihin ng VARS? Volt amperes reactive. And for an inductance, that is I squared XL. And for a capacitance, it is negative I squared XC. Very important yung negative, no? Negative. Basta alam mong capacitor, dapat lagyan mo ng negative sign yung reactive power. Apparent power is just the product of the RMS value of voltage times the RMS value of current. That is your apparent power. And the power factor is P, itong P, divided by S. And that will be the cosine of theta V minus theta I. And you have to specify, when you specify a power factor, pag tinanong kayo, no, what is the power factor of this circuit? After giving the answer, you have to specify whether it is lagging or leading. All these quantities, P, P's of R, Q, Q's of L, Q's of C, S, PF, these are not phasors, neither are they complex numbers. These are just all scalar quantities. Hindi sila phasors. A lot of times I see people, no? Siguro nalilito na kung ano ba yung phasor, ano yung hindi phasor. None of these quantities are phasors. What is a phasor? Remember, a phasor represents a sinusoidal quantity. No? It is vector in the complex plane that is rotating, in the counterclockwise direction. And none of these are phasors. Okay? So lahat ng derivations na ginawa ko are just for me to come up with these relationships which you should remember. Let me ask you a question. If I have a resistive circuit, what is my power factor?
1.
Does anybody contest that? Bakit 1?
In phase po sila. So,
Yeah.
theta V minus theta I is 0.
Yes, that's right, no? If I have a resistive circuit, my power factor is 1. What does that mean? That means that, my voltage and current are in phase. No? That means that S is equal to P. S is equal to P. My volt amperes and my watts are actually equal. Okay. Okay, remember the Phasor diagram? The Phasor diagram gives you a snapshot of the relative position of your phasors in the complex plane at time t equal to 0. So if this is my time domain expression for voltage, this is the equivalent phasor, v sub m over the square root of 2 at an angle theta v, and then this is the equivalent phasor of my current, and then if I leads v, so this is a case where I leads v, I leads v. This is what my phasor diagram will look like. So this is leading power factor, no? Itong situation na to, leading power factor. Right? Nauna yung V nauna yung I kaysa V. If your power factor is leading, the load is absorbing negative reactive power. No? The load is absorbing negative reactive power. Or you can say it the other way. The source is delivering negative reactive power. So you have the perspective of the load or you have the perspective of the source. If you're talking about the load, pag leading power factor, the load is absorbing negative reactive power. If you're talking about the source is delivering negative reactive power. And this happens when the load is capacitive. In other words, if I get the equivalent impedance of my circuit, it has the form R minus JX. Now, this is a situation now where you have lagging power factor. Lagging power factor, the load is absorbing positive reactive power. The load is absorbing positive reactive power. From the point of view of the source is delivering positive reactive power. And this happens when the load is inductive or of the form R plus JX. Now, the relationship between P, Q, and S, that can be described by what we call the power triangle. In fact, when all else fails, this is all you have to remember. It makes it easy to remember, no? If you cannot remember this, or if you think you're going to have a hard time remembering this, ito na lang yung tandaan ninyo, no? That you have a right triangle, okay? Your the difference in angle between your voltage and current is theta. So theta is theta V minus theta I. No? Remember, no? It's always the voltage minus the current. The angle of the voltage minus the angle of the current. Okay. And then opposite that angle, you have your reactive power. Adjacent to that angle, you have your real power. And the diagonal is equal to your apparent power. Okay, if you know this triangle, then you know that S is equal to the square root of P squared plus Q squared. Okay, and tangent theta is equal to Q over P. Right? Okay. And if you know S, then how do you compute for P? P is just S times the cosine of this angle. And Q is equal to S times the sine of this angle. So that's really all you have to remember. No? This power triangle. Are there any questions so far? Any questions? Okay, now here's the thing, ano? Sometimes ang ibibigay sa iyo is yung power factor. Okay? So sometimes instead of theta, what is given is your power factor. So that's easy, no? Theta is just the arc cosine of your power factor. Okay. However, depending on whether the power factor is leading or lagging, you have to assign the correct sign for Q. No? In other words, if leading, if your power factor is leading, then Q should be negative. And if lagging, then Q should be positive. And that's where a lot of times students make mistake. No, they forget. Pag minsan, no, binibigay, okay, this is a device with a certain power factor. The power factor is leading. Nakakalimutan nila gawing negative yung Q. And then all of their computations now are no longer correct. But at the end, you just have to remember this triangle and note, if I know any two quantities in this triangle, I should be able to get the other two. If I know any two quantities in this triangle, I should be able to get the other two. In other words, no? If I know P and Q, I can determine S and theta. If I know S and theta, I can determine P and Q. No? If I know P and theta, I can determine S and Q. So, sorry. No? You just need to know two quantities to determine the other two. Are there any questions? Okay, now here's another definition. Complex power. The product of the phasor voltage and the conjugate of the phasor current is defined as the complex power S. So what is that? S is the product of your phasor voltage multiplied by the conjugate of your phasor current. No? So this symbol, this is the conjugate of I. And we can show that, no? So ito yun, no? S is equal to the product of your phasor voltage and the conjugate of your phasor current. Okay. This is where it gets a little bit misleading, no? Linalagyan natin ng parang arrow dito to indicate that this is a complex number, but this is not actually a phasor. No? This is not a phasor. This is just a complex number. It's just, we're just putting this arrow to differentiate S from apparent power. So when you say S, okay, this is complex power. When I just say S, this is apparent power. No? So this is complex. This is a scalar quantity. So if I carry out this computation, V times the conjugate of I, this is V. This is the conjugate of I. How do you get the conjugate? You just make the angle negative. Then you carry out this complex multiplication. This is going to be VI at an angle theta V minus theta I, right? If I convert this to its rectangular form, this is VI cosine theta V minus theta I. That's the real part. And the imaginary part is J VI sine theta V minus theta I. So take note that this is equal to P by definition, and this is equal to Q by definition. Thus, if you carry out this multiplication, V times I conjugate, you're going to get an expression for complex power, which is P plus JQ. Okay, so let's take an example. Very simple circuit. I have a sinusoidal voltage source, and then I have an 8 ohm resistor in series with a 0.6 Henry inductance. I want to find all P's and Q's. Ano ibig sabihin ng all P's and all Q's? No? I want to find the power delivered by the source, the power absorbed by the resistance, the power absorbed by the inductance, the reactive power delivered by the source, the reactive power delivered to the resistance, and the reactive power delivered to the inductance. That's all P's and all Q's. So I start by transforming my network. So hindi pa kayo hindi pa kayo makakaiwas sa Phasor method dito. So you transform the network. So this is my transformed network. This is my voltage. My total impedance is 8 plus J6, which is 10 at an angle 36.87 degrees. I can compute for the Phasor I. So this is actually a Phasor. Kulang ng. Okay. So the Phasor I is just V over the total impedance. So this is 7.071 at an angle minus 36.87 degrees amperes. Okay. Okay, here. So what are the power and reactive power delivered to R and to L? Okay, remember that I don't have any power. When you say power, pag sinabing power lang, implication is this is real power, no? Real power. So without any qualifier, pag sinabing power, that means real power. Remember, I don't have any real power delivered to L. My real power will only be delivered to R. And I don't have any reactive power delivered to R. My reactive power will only be delivered to L. And if you already know the RMS value of your current, kasi dito, alam na natin, no? I RMS, which we just say is I, is equal to 7.071. No? Remember, we're just dealing with the RMS value, no? Not with the Phasor quantity. So if I already know the RMS value of I, then the power delivered to my resistor is just I squared times R, which is 400 watts. And the reactive power delivered to my inductance is I squared times XL, which is 300 volt amperes reactive, or 300 VARs. What about the source? The source, I have to use the formula. Power delivered by the source is VI cosine theta V minus theta I, because all I know is the voltage and the current. And the reactive power delivered by the source is VI sine theta V minus theta I. So those are the formulas that I have to use. Okay, so VI cosine theta V minus theta I, the magnitude of V, what is the magnitude of V? It's 70.71. The magnitude of I is 7.071. 70.71, 7.071, cosine of, okay, the angle between your voltage and your current is 36.87 degrees. Okay, I have 0 degrees here. My current is minus 36.87. So theta V minus theta I will be 36.87. And you get 400 watts. Same way you get 300 vars for the reactive power delivered by the source. Note that the power delivered by the source should be the power absorbed by the load. And the reactive power delivered by the source should also be the reactive power absorbed by the circuit. So this is one way, no? This is one way of solving it. The other way is we could have used the complex power formula. No? S is equal to V times I conjugate. So this is V, 70.71 at an angle 0. This is the conjugate of I. How do you get the conjugate? You make the angle negative. Okay, and that ends up being 500 at an angle 36.87. If you convert that to rectangular form, that's 400 plus J300. We know that this is P and this is Q. So many ways of solving this. I already mentioned this. Conservation of power applies to both real and reactive power. So the total real power supplied by the sources should equal to the total real power absorbed by the passive elements. In this case, it's only the resistor that's absorbing real power. The total reactive power supplied by the sources should equal to the total reactive power absorbed by the passive elements. In our example, it's only the inductance. And that's my last slide for today. So on Thursday, all we're going to do is take up examples. Maybe we can take up some of the examples that are in the course notes that were delivered. Again, no, if I may emphasize, we did a lot of derivation. But at the end of the day, this is really what's important, that you understand these relationships. Are there any questions? There seem to be no questions. Any reactions? Wala. So ang Meralco, ang sinisingil ng Meralco sa atin is just P, no? Your real power. That's what Meralco charges you for. In other words, your electric meter in your house really only measures real power. Okay. But reactive power is quite important, no? Because what happens when your reactive power is very high? If your reactive power is very high, ang ibig sabihin nun, no? Yung instantaneous power mo, ang lakas ng fluctuation. Your average power might be only this much, but if you take a look at the graph versus time, it's fluctuating very, very high, no? That is your reactive power. Fortunately, if you have high reactive power, fortunately, that will not go into your electric bill. That is if you're a household. But if you're a factory, they make you monitor your power factor. And if your power factor is low, kasi pag mababa yung power factor mo, that is when your reactive power is high. No? The maximum power factor is 1. If the power factor is 1, you have a resistive circuit and your reactive power is equal to 0. As your power factor gets lower, your reactive power gets higher. Meralco will charge you, for example, a penalty if you exceed or if you go below a certain power factor. So that is how we are billed electrically in our homes. Now you have a lot of devices in the market that say, okay, plug this into your home, and you will save electricity. Actually, most of those are fake. No, a lot of them are just power factor correction devices. They correct your power factor, but if you're a home, hindi ka naman pinapenalize for low power factor. So most of those devices are actually bogus. I haven't seen any genuine device yet like that in the market.
Sir,
Yes.
question po. Ano pong implication pag yung power factor po ay -1?
Ang power factor mo is the cosine is always positive, di ba?
Po, sir.
No, sorry. Maybe hindi tama 'yon, no? Your power factor yung power factor mo will always be from 0 to 1. It doesn't end up being negative. Saan ka nakakita ng power factor na -1? Sino yung nagtanong, no? Where did you encounter yung -1 na power factor?
Ay, ano lang po, baka lang po meron.
No, usually your power factor is between 0 and 1. If you recall yung angle between your voltage and current, no, it will always be an angle between 0 and 90 degrees. No? Because if your circuit is purely if your circuit is purely inductive, it will be 90 degrees. If it is an inductive circuit, that is a resistance plus inductance, it's going to be between 0 and 90 degrees. No? If your circuit is purely capacitive, that's minus 90 degrees. If it's a resistance plus a capacitance, it's anywhere from 0 to minus 90 degrees. So in all those cases, your power factor will never be negative. It will always be positive. Any other questions? So my advice to you, don't get intimidated by, if I may go back, because if you take a look at the course notes, pag tinignan nyo yung course notes, ang haba-haba ng derivations na ginawa, no, dito, from this expression, to get to this expression, it did a lot of derivations. Which is okay for you to understand, no? So that alam nyo na totoo, no? Na hindi nambobola yung notes. But don't be intimidated by that, As long as you understand how it was derived, then you don't have to, after that, you don't have to remember how it was derived anymore. Okay? And then the only reason why I came up with this expression was so that I could compare it with the expressions for your resistance, so that I could compare these two and come up with this conclusion, so that I could compare these two and come up with this conclusion, and then finally, so that I could compare these two to come up with this conclusion. Right? And then after that, this is really all that matters. This is really all now that matters. So you have to know this very well, no? Ito mga power relationships na to. And also, very important is complex power. The concept of complex power. Okay? So any other questions? So wala na tayong ano, no. I'm not going to maybe I'll do a short review on Thursday, but on Thursday it's really just going to be mostly examples. By the way, no, in the real world, the problems that you encounter in AC systems are the problems that you will encounter this week. Most of the time. Most of the time, yung mga maenkwentro niyo sa industry, for example, those are the problems that are going to be solved this week. So with that, yeah, I'll close the session. You can leave. I'll close the session when the last person logs out.